Welcome back. This is Larry Benko W0QE, and this video is about coefficient of coupling and various ways to measure it. Coefficient of coupling is the fraction of magnetic flux from the current in one coil that links to another coil. It's usually designated by the small letter K, has no units, and is a real and not a complex number. Coefficient of coupling is pretty constant with frequency, and we typically measure it at a lower frequency than we intend to use the circuit at, so that effects like parallel capacitance across a winding do not affect our ability to measure it. It has absolutely nothing to do with circuit efficiency or power loss. It changes the circuit, of course, but it has nothing to do with circuit efficiency. The range is between 0 and 1, but SimSmith allows us to have negative values, and I'll talk about that in a few moments. Looking at the model here, what we see is two windings. This is shown as equal number of turns, but they don't need to be equal number of turns by any means. We have a certain coil over here that we're going to, say, put a current through. A certain percentage of these turns, as shown by K, which is the fraction of the total number of turns, these will couple 100% to the same fraction on the other side. So if this is twice as many turns, this will be, and this is, say, 60.6. 60% of these turns couple perfectly to 60% of these turns. 40% of these turns and 40% of these turns do not couple at all. Now, this does not represent reality, of course, but it's the best we can do easily. And the reason for that is, in a real inductor, all the turns would couple with some value. Some may couple better than others, but nevertheless, that's a very difficult thing to try to analyze. By saying a certain percentage couples completely and a certain percentage couples not at all, we can build a circuit and get results that are pretty good. And it's harder to achieve good performance in coefficient of coupling as the physical size of the structure becomes larger. And that's typical of pretty much everything in RF. And ultimately, coefficient of coupling really doesn't even matter in a circuit. It's the circuit performance that matters. You can tune out leakage inductance for narrowband uses, and for broader band uses, I showed in video number 85 that an auto transformer in many cases performs better than a conventional transformer with a lower coefficient of coupling. Shown here are two coils, 5 turns each, wound fairly close together, and they're aligned with each other, and they're both wound in the same direction. If we start right here, we see the winding going this way. We start right here, we see the winding going this way. 5 turns. This would produce phase dots that would be in this orientation like this. Or you could put the dots on this side and this side, and that would be the same too. I have a generator that comes in and drives this. I have an oscilloscope that's looking at the voltage. This is the ground probe of the oscilloscope, and the hot end of channel 1. Channel 2 sits here and here, and I see the two phases, the two voltages in phase. And the reason I see them in phase is because the leakage inductance is not enough to cause any phase shift with respect to the high impedance that the scope probes produce. These were done at 5 megahertz, and we see a coefficient of coupling of about 0.18. And that's what you would get typically. The core here is nothing more than a thin piece of G10 fiberglass material, so it doesn't really have any permeability. And that's kind of typical of an air-wound air core inductor. Now over here I've done the exact same thing, except I turned the orientation of the direction. So the winding here, no, I'm sorry about the blurring. This winding starts and goes this way. Over here it starts and goes the other way. So that effectively turns the phase dot around. And we see out of phase, where these were in phase, for the same scope orientation. I could have, of course, put the ground side of the scope over to here and the hot side of the scope over to here, in which I would have seen in this plot. But I just thought I'd mention the fact that when you wind a coil in the opposite direction, that does change where the phase dots are. So take it for what it's worth. We're going to show that in just a moment, the usefulness of being able to sweep with negative coefficient of coupling. In this SimSmith schematic, I have a generator, I have a load, and I have a single component in a ruse block. And that component is a 5-pole low-pass filter. These values are nothing special. I cobbled them together. They're all even values. But I get roughly a 10 megahertz low-pass filter. And a 10 megahertz low-pass filter with reasonable passband SWR, reasonable stop band attenuation. And I wanted to explore what would be the effects in the filter if I had slight coupling between these two inductors. If I build this, I'm going to have a little bit of coupling between these, and I can control the coupling to be one. The phase dot can be here or here relative to this inductor, and let's see if that makes any difference in our circuit. So if I change the coefficient of coupling from 0 to 0.025, we see the stop band getting worse. If I change it to minus 0.025, we see the stop band getting better. Now, you can't continue on too far because the SWR curve gets worse in the passband and stuff, but a little bit of coupling. We expect a little bit of coupling, but not very much. So I'm really better off to go not this direction, which is a positive coefficient of coupling, but down here with the negative coefficient of coupling. And I could have done, if I'd drawn the inductor with the dot here, I would have seen the exact opposite effect here. But negative coefficient of coupling is useful when I want to move in a sweeping operation. I want to change the schematic as to how the phase of the inductors is relative to each other. And just as a real quick another point, if I were to sweep the coefficient of coupling, it doesn't matter what this value is now. We're sweeping down here from minus 0.05 to plus 0.05, 3 steps only, so I see 3 curves. Now you might do this and see something that looks like this. And this is because SimSmith, when I sweep multiple variables, generally does a grid pattern. If I want these to be lines, you can see the lines inherently underneath here, but I see lines going this way also. I can sweep my own lines by manually controlling the power plot and the SWR plot to be lines rather than grid or dots or anything else for both the power at the of the filter at the load and the input impedance, which I'm plotting as SWR. But the point was, it's the reason SimSmith allows us to have a negative value for coefficient of coupling, even though there really is no such thing. Method number 1 of measuring coefficient of coupling will be something I'm going to call the voltage method. And before we do that, though, let's compare these two circuits quickly. This circuit is an inductor and another inductor that are coupled together in typical SimSmith fashion, where we give it a coefficient of coupling between 0 and 1, and SimSmith does all the work. We can also do this specifically where we define this to be similar to this model, where we will say that this fraction of the inductance couples perfectly, and this fraction is leakage inductance, and we will get exactly the same answers. Now, this model, while it looks to be a little bit more complicated, it also, I think, is a little bit easier to understand. So we're going to use this model, remembering, of course, that this connection between the leakage inductor and the coupled inductor is not available to actually be measured in a physical circuit. So continuing with this circuit, we see that we have a fractional piece of the total inductance, which is K12. That's the coefficient of coupling. This fractional piece couples perfectly, coefficient of coupling of 1, and piece that doesn't couple is leakage inductance, hence the L on the suffix, and C is the coupled inductance, which couples perfectly. If we were to apply a voltage from W1 to ground, we would see that these two inductors represent a voltage divider. So in this case, I've got a coefficient of coupling of 0.9, so 90% of the voltage will appear here. That means that over here, we will get a 100% coupling between these two inductances, and we will have a leakage inductance. This leakage inductance will not enter into the equation provided that we look at the voltage out here with a very, very high impedance. This circuit is functionally identical to the previous one, although I changed a little bit of the plotting just to hopefully make it a little bit clearer. We're going to drive the circuit with a generator, 50 ohm output impedance. I terminated it. It doesn't necessarily need to be terminated in this case at all. We're going to measure the voltage independent of whatever's on the generator side of it. A capacitor here will include any capacitances across this winding and any measurement capacitance that we might want to use. Likewise, this capacitor is the same way, and we have a high impedance load. So if we look at this, what we would do in reality, we'd put an oscilloscope probably across here. Now, if I use 2 traces of an oscilloscope, I have the problem with the 2 channels being slightly different. probes being different, but if I take channel 1 and put it across here and I measure voltage, and then take channel 1 and move it over to here and measure voltage, let's see what that means. Putting channel 1 here with a times 10 probe results in a couple of picofarads of capacitance. And that's okay. Let's see what the effect of that is. So I've calculated the voltage across the blue trace is the voltage across the input, which is basically just the voltage across these two inductors. And I'm doing this in two ways. In SimSmith version 16.8, there's a new feature. So we used to say the magnitude of this number, which was L1, and just as, for example here, just if we're doing just this piece of the inductor, we could say L1L dot V, which is the voltage across that inductor, and the magnitude of it would turn it into a number that was not a complex number. Or the new format in 16.8, the old format still works in 16.8, but the new format is L1L dot V dot capital M for magnitude. So I've done that a couple different ways here, but nevertheless, the first plot plots the magnitude of the voltage across here. The second plot plots the magnitude of the voltage across L2. And the third plot does what you see in books often. You often see a term, when they talk about coefficient of coupling, they'll say the output voltage versus the input voltage is equal to the coefficient of coupling times the square root of the ratio of the inductances. And if we solve that for K, we get this formula right here. And I put that formula right in this plot mechanism. So we're going to calculate. I'm calling the plot calc K, which is the red plot, and it's going to be the voltage across L2, the magnitude of it, divided by the voltage across L1, the magnitude of it, times the square root of the total inductance for L1 divided by total inductance for L2 in parentheses. And when we do that, I plotted the two voltages too, but they aren't necessary. We're going to sweep this circuit from a coefficient of coupling of 0 to 1, and that is real. That's the sweeping that SimSmith's going to do. We're going to calculate this based on the voltages that SimSmith gives us back. So with 2 picofarads, or let's just make this even more, so make it 5 picofarads here, it shows that if we have a coefficient of coupling of 0.9 in reality, our calculated coefficient of coupling is 0.9 also, assuming absolute measurement accuracy. Also means if we have a calculated coefficient, or an actual coefficient of coupling of 0.5, our calculated coefficient of coupling is 0.5. Nice straight line, everything's good. Now we take our oscilloscope, which measured the voltage here, and we're going to take the same channel, so we're going to turn this capacitance back to 0, and move it over to here to be a couple picofarads, and watch what happens to the red curve. It gets a bow in it. That means now measuring this voltage on the output and then putting it into the formula causes us an error. Up here at 0.9 for a coefficient, it's just fine up here at a coefficient coupling of 1, but at 0.9, a real coefficient of coupling of 0.9 is calculated to be 0.906. A real coefficient of coupling of 0.5 is calculated to be 0.515. If that's too much error, then you kind of are stuck with this not being a very good method to measure coefficient of coupling, unless you're capable of doing it with a lower capacitance type probe. We can also drop the frequency down. And as we drop the frequency down, we can see, let's drop it down to say about 3 megahertz, we see that the resulting effect of this capacitance is less. So at 3 megahertz, or actually 2.8 there, we have a coefficient coupling of 0.5. In reality, we calculate it as 0.501, which is awfully close. So this is why we end up often making the measurements at a lower frequency. Now, if there's capacitance across the windings, we'd have to include that too. On this side, it doesn't affect anything. On this side, it does affect it somewhat. And we start to see some small changes there. But it does mean we have to be a little bit careful. Now, it's a function of what the inductance values are and everything else, but we can use SimSmith to help us in a circuit real quickly determine whether or not this is a good way to measure coefficient of coupling or not. Now, what if we have an auto transformer? An auto transformer would have a different circuit than this, but we can still measure it. What we end up doing is we end up with an auto transformer. Think of this point on the inductor connecting up here, and then we're going to drive this circuit just across one inductor, not across the inductor to ground. But this connection is effectively an auto transformer. You only have 3 terminals. You have one terminal You have this other terminal, which is common. This is ground now, actually. And then there's the third terminal. You can still make the voltage measurements across it. It means when you put your scope over on this side, you need to put when you measure this, you need to put your scope ground probe at the center point between the two inductors and then measure the voltage on the input and the voltage on the output. But that'll work just fine. We see the same curve as before. So this is a reasonably good way to measure coefficient of coupling, and you see it in textbooks all the time. Second method of measuring coefficient of coupling I will call the open-short method. You see it in textbooks also. What it tells you to do is to measure the short circuit inductance with the two coupled coils. So we'll short this side out. We'll measure the inductance on this side. We'll divide it by the open circuit inductance, which is just the inductance here with this side open. And that's equal to 1 minus the coefficient of coupling squared. Or we can rewrite it in this form. So to see what we have in this circuit, we need to get Sim-Smith to give us the measurement of inductance right here when this side is shorted. The open circuit inductance is just the given value, which is 10 microhenries in this case. The short circuit inductance is the impedance looking in here, and we want the imaginary part of that impedance divided by 2 pi f. So if we do this like we would do it in version 16.8, we could say A dot capital Z, which is the impedance right here, looking to the left, dot X, or actually dot capital I also works in version 16.8 for the imaginary part of the impedance. And we'll divide that by 2 pi f, and we'll convert megahertz to hertz, and that gives us inductance. Now we could also do it this way, which is the version 16.7 way of doing it for the imaginary part of A dot Z. Either one of these is acceptable. And I've saved these in a hidden variable so I don't see it plotted out here in the parameter window. It doesn't mean anything less or more. It just means I just decided not to show it here. Now we're going to plot some stuff. The first thing we're going to plot is the inductance in open circuit. Well, that's nothing more than plotting the value of L1, which is 10 microhenries. Then we're going to plot the short circuit inductance that we see, and we see that that goes to 0 when the coefficient of coupling is 1. It goes up to 10 microhenries when the coefficient of coupling is 0. Coefficient of coupling 0 means the coil might as well not be there. And that's what you'd expect. It's not a linear curve. And we will plot in the red curve here the calculated value, and that's just me plotting this formula right here. And when we do that, we see the same thing we had before with the voltage method. We see a nice straight line. So we're going to sweep, Sim-Smith's going to sweep the coefficient of coupling from 0 to 1 in reality. We're going to use the measured values we got, and we're going to calculate the coefficient of coupling from those values and see how we did. And what we say is, again, it looks perfect. Now, let's go back and add some anomalies. If there's a little bit of capacitance across this winding, just a couple picofarads, what we start to see is this circuit start to really go away. It still does a very, very good job up here for high coefficients of coupling, but it does not do a very good job for low coefficients of coupling. But not up here at 0.9, let's see if I got there. The value of 0.9 is in reality, we're measuring 0.893. That's not too bad. Up here, even higher, if it was 0.97, we're at 0.9699 effectively. So this does a very good job up at the higher values of coefficient of coupling. You have to be very aware of using it at the lower values of coefficient of coupling. And the voltage method is much better at that for that purpose. But nevertheless, this is a super easy way of doing it. What happens if this is an auto transformer? Well, if it's an auto transformer, again, who cares? You got the windings connected together. It doesn't affect the coefficient coupling or anything else. So in this case, treat this for what it's worth, but this is another method that's mentioned. And again, if we drop the frequency down, look what happens. As we go to lower and lower and lower frequencies, the effect of this capacitance becomes less. For the third way to measure coefficient of coupling, I have a circuit which I've never seen published, but it's really not that difficult. It's based on the definition of coefficient of coupling and a bunch of algebra, and you come up with a formula for the calculated coefficient of coupling looking like this. The total inductance, which is the inductance measured from this point to this point, minus the inductance of this inductor, minus the inductance of this inductor, that quantity divided by 2 times the square root of the product of this inductor and this inductor value. You might say, well, that's a lot of work, but it's just 3 measurements. You measure from here to here, you measure from here to here, and then you measure from here to here and measure the inductance. And if you do that, and if you want to look at this a little more details, just pause the video for a second. We see again the same nice straight line curve for calculated coefficient of coupling, and we're sweeping again the coefficient of coupling on the horizontal axis, and everything looks good. I've also plotted the effective inductance of from here to here. So what happens if I have a little bit of capacitance? If I have a little bit of capacitance, let's close that off. A couple picofarads of capacitance, we start to see. In this case, this is predicting a coefficient of coupling above 1 slightly. Well, that's the way it works. And a coefficient of coupling, this changes the minimum coefficient of coupling to be greater than 0. The maximum coefficient of coupling is above 1 again. But if we do this, let's go back to where we were. If we do this, as we did in the other cases, at lower and lower frequencies, pretty soon we come up with something that looks pretty much what we had before. Again, we can tolerate some reasonable capacitances, and we get a very nice straight line. And that means our calculated... So here we are with an actual coefficient of coupling of 0.5, calculated coefficient of coupling of 0.503. Here's 0.9, it's 0.904. These are pretty close, and this might be a little bit easier to do. It does involve, if you have two coils that were wound separately, it does involve connecting them together at a center point to make the measurements, but that's the case automatically with an auto transformer. So anyways, I just thought I'd propose this one as another possible choice. And in conclusion, some typical coefficients of coupling would be for air-coupled coils where the coupling is desired between the coils. 0.1 to 0.6 are typical coefficients of coupling. For air-coupled coils where coupling is undesired between the coils, you will typically mount the coils as far apart as possible, and you'll try to mount them at right angles. If you mount them at right angles and you keep the coils separated by about a diameter apart, you can get numbers like 0.01 pretty easily. For ferrite or powdered iron cores where the coupling is desired, typically between 0.5 and 0.99. It's pretty hard to achieve anything higher than 0.99, and you never wind two coils on a ferrite or powdered iron core and expect not to have coupling of some sort. And if you really desire to have a lot of coupling, you resort to things like bifilar winding, trifilar winding is shown here, trifilar winding with a turn missing. In a trifilar winding, you would take two of the windings and put them in series, perhaps scramble wind them. There's lots of different ways to do the winding, but the goal in all these techniques of winding is to increase the coefficient of coupling. Most designs desire a high coefficient of coupling. If you look at any commercial designs, coefficient of coupling almost is never good enough, and there's almost always some kind of a circuit compensation involved also beside trying to get good coefficient of coupling. Without good coefficient of coupling, you can't really make the circuit work really, really well, but compensation definitely is a big help. If you've enjoyed this video, let me know, and there'll be more. Thank you very much.